yesterday we talked about the circumstances, sort of, under which a series, an infinite series specifically, has a sum. And we said yesterday that one way to determine that sum is to see if a sequence of partial sums actually approaches the limit. And those are the exercises that you had on your homework last night. You had to find 4, 5, 6 partial sums, see if those partial sums approached a number. If they did, then that number was actually the sum of your series, so it was kind of neat. You get another method for doing that today, okay? And true story, that second method, usually a little bit easier. What we're going to go ahead and say, for the sake of our Honors Algebra 2 course, is, fun fact, your series is only going to have a sum, an infinite series that is. Your infinite series is only going to have a sum if 2 conditions are met. Condition number 1, it's geometric. If it's not geometric, in other words, if it's arithmetic or neither, you're going to keep adding on numbers or just kind of being random about things. And in which case, you won't have a sum. But if it's geometric, like when we were having the paper yesterday, we could glue things back together to get a sum. So condition number 1, under which your series will have a sum, is that it's geometric. Condition number 2 that must be met for your infinite series to have a sum is that the absolute value of the common ratio must be a number that is less than 1. So if those 2 conditions are met, you can go ahead and use this formula right here. So if you have a geometric series where the absolute value of your common ratio is a number less than 1, this is the sum formula you're going to go ahead and use. Just to give you a little glimpse into where this formula came from, I'll go ahead and show you. You don't have to write this part down. But this formula here looks a whole lot like our formula for a finite geometric series, where we took the value of our first term, subtracted the product of our nth term and our common ratio, and then divided by the difference between 1 and our common ratio. These formulas look pretty similar, don't they? Except this one, has that a sub n times r in it. But they're more or less very similar. And it's kind of common sense as to why we can't have this part if we're talking about an infinite series. A sub n, this guy right in here, that indicates that there's a last term. Well, you can't use this formula if there's no last term. Infinite series go on and on and on forever. There's no nth term. There's no end to that series. So you can't possibly use this formula. It would make no sense to do so. So if you have an infinite geometric series under which your absolute value of your common ratio is a number that is less than 1, we're going to use this guy today. All right, we have basically 3 examples for that formula. The first thing we ultimately have to decide is, does the geometric series actually have a sum? And if so, what is that sum? So that's what we're going to go ahead and do. Are you missing the paper, Ryan? Are you missing this page? Okay. If you need an extra page because the copy center, like the back page fell off of some people's packets, there are extras in the back. But yeah, it's just these last couple examples and then that's it. All right, so we're going to go ahead and take care of this last example here. It says, does each geometric series have a sum? If so, what is it? Okay. Step 1, and here's what I want you to take a moment to do. Notice they already told us that circumstance number 1 has been met. Do you see how they just come on right on out and say, hey, these are all geometric? That is true. All 3 of these are actually geometric. And that's really the first circumstance that has to be met, or the first requirement that has to be met in order to use our sum formula. So that part has been taken care of. Now we have to check for the second requirement. We have to check the values of our common ratios in each of these particular series up on the board behind me. So what I want you to do right now, sort of is like a warm-up, I want you to take a minute and identify the common ratio in number 3, number 4, and number 5. Okay? So take a minute and do that. I'm going to hit pause. Common ratio for number 3. 0.2. That's also the same thing as 1/5, either or. Fair enough. Okay. I'm just going to get the common ratios down, then we're going to take a look at it, okay? All right, so that's the first one done. Hey, Sally, what'd you get for your common ratio for number 4? That's correct. Or you could say, you know, 0.666 repeating, or, you know, 0.6 with a hat on it, however you want to work it out. And then Will, number 5, what's your common ratio there? Yeah, it's just sitting right next to the variable exponent that you have there. Okay. So now what we're going to do is we're going to run the test to see if we can actually use that formula you just copied down a few minutes ago. Does anybody have any questions about how these common ratios came about? We're good there? Okay, so let's scroll back up to the top here. All right, so please understand there's 2 requirements for your series to have a sum. The first one was geometric. It has to be an infinite geometric series. And now we need to look at the value of our common ratio. In order for us to use the formula, we have to just check to make sure that the absolute value of your common ratio is a number that is less than 1. So right now in problem number 1, I'm looking at 0.2. Just for fun, I picked the 0.2. I'm looking at 0.2. That is the value of my common ratio. Now I have to take the absolute value of 0.2. What is the absolute value of 0.2 or 1/5? Well, yeah, 0.2. Remember to find an absolute value of a number. It's just the distance it is from 0 on the number line, or just drop any positive or negative that's in front. It's just always the positive value. So the absolute value of the common ratio is going to be 0.2. All right. So now we have to ask ourselves, is that a number that's less than 1? Why, yes, 0.2 is a number that's less than 1. So this series will have a sum. With that in mind, now I can use my sum formula. So since the absolute value of our common ratio was a number less than 1, we can go ahead and proceed and use our sum formula that we just jotted down. The sum formula says take the value of your first term, in this case it will be a sub 1, and divide that by the difference between 1 and your common ratio. So a sub 1 was 4. We said our R value was 0.2 or 1/5. So this is like 4 over 4/5, which is the same as 4 times 5 over 4. So the sum of this series is 5. Initially, I looked at 0.2. Remember that if there's a typewritten fraction in the problem, you should be trying your darndest to show all of your work and your answers as a fraction. So that's why I bailed out. I didn't have a calculator handy. I didn't want to use the decimals. The fractions are a little bit easier to work with in this problem. So yeah, see all my work there, fraction work. So yeah, our sum is 5. Does anybody have any questions about that? All right, let's do it again. Number 4, first thing I have to do is look at the absolute value of my common ratio. The absolute value of my common ratio is going to be the same thing as the absolute value of negative 2/3 in this case. So the absolute value of my common ratio is 2/3. And 2/3 is less than 1. So yes, this series will have a sum. Which means that now I can use my sum formula. My sum formula says take the value of the first term, and since we're starting with the first term of 3, that's, you know, my first term. So my first term is 3. And I'm going to do 1 minus the value of my common ratio, which is a negative 2/3. Watch your sign. It is often enough, not rampant, but often enough, where students will make a sign mistake on the bottom. Notice the formula, just to scroll back for a second, notice the formula has R in it. Not the absolute value of R, but R is in the formula. So you're taking your original R value and plugging it into the formula, not the absolute value of R. Make sure you don't confuse that idea. So yeah, do you see I have 1 minus a negative 2/3 because the common ratio itself was negative, which means I'm going to add on the bottom. So I have 3, and then 1 2/3 is the same thing as 5/3. And whenever we divide by fractions, you might recall that we actually multiply by the reciprocal of your divisor. So we get 9/5, or that would be 1.8 if you were a decimal fan. Questions about that? All right, one more. This is my last one. My last example. You did it. After this, you listen to all of my examples. Number 5. So we have sigma notation. It starts on the bottom at n equals 1 and goes to infinity when we have 0.4 raised to the n minus 1 power. I think, Will, you gave us this common ratio, right? Yeah. How'd you know that it was 0.4 again? Yeah, it's the base for the variable exponent. Good job. Yeah, it's kind of right in the problem. So now what I need to do is write my sum formula there. Notice, watch out for your sigma, or the value on the bottom of your sigma. In this case, my first term, they're saying it's in position number 1. But if n equals 2, your first term is a sub 2. If they say let n equal 3, your first term is a sub 3. They say let n equal 25. Your first term isn't a sub 1, it's a sub 25. So this number isn't here for decoration. As you work through your review problems tonight and then your review guide problems tomorrow, make sure you pay attention to the number on the bottom of sigma. Ultimately, it does affect how you plug numbers in to your sum formula, so watch out for that. So in this case, the number on the bottom of sigma is 1, so my first term is a sub 1. And then 1 minus my common ratio. So a sub 1 is a value I have to find. In order to do this, I'll just take my explicit formula there and plug in 1. I end up with 0.4 to the 0th power, and that's just 1. So I did take a moment to find the value of my first term by plugging n equals 1 into my explicit formula, and then I followed my order of operations to evaluate. The value of my first term is now 1. So I have 1 over 1 minus 0.4, which is the same thing as 1 over 0.6. 0.6 is 6/10. Divided into 1, you get 10 over 6, which is 5/3. So that's my sum there. And that is it. Questions about that? Because that is our lesson for today. Big idea in today's lesson, we do a test to see if a series has a sum. It has to be geometric with an absolute value common ratio less than 1. If those two circumstances exist, your infinite series has a sum, and you can find it. Instead of doing your sequence of partial sums, you can actually find it by using our sum formula, a sub 1 over 1 minus r. And that's it. Your homework tonight is the infinite series review worksheet. You picked it up when you walked in the back. In addition to that assignment, I do want you to go ahead and take a look at the review assignment for your Chapter 12 test. I want you to come in tomorrow with questions about that review assignment. So as you look at that review assignment, you kind of want to look at it critically and say, hey, you know, is there anything on here that I can't do very well? Is there anything on here that I would need help with? Because those are the questions you can ask about for tomorrow. Traditionally, like I said, the tougher problems on the test are where you have to find or write sigma notation for a geometric series that's finite, and you have to solve for that n on the top using a logarithm. So just kind of keep an eye out for that. If you need a little practice with that, tonight's a good night to go ahead and give that a whirl. But in addition to the worksheet, you're going to go ahead and look at the review assignment for Chapter 12, okay? And then with that, a